What are the true secrets of the asteroids in our solar system? Dear traveler, greetings. Today we delve into a realm of rocks and silence, the raw remnants of the birth of the solar system. A world of scattered fragments, drifting between Mars and Jupiter, but also far beyond the known boundaries. Asteroid belts, frozen chaos, or a treasure trove of cosmic memories. And one question remains: are they merely sterile debris, or the forgotten keys to the origins of our world? But before embarking on a new adventure, don't forget to like the video and subscribe to the channel so you won't miss anything. Thank you and safe travels. If the main belt is located between a little over 2 and 3 astronomical units, there is a mini ring below it that deserves attention. This zone, called the Hungaria population, extends from about 1.8 to 2 astronomical units. To understand their grouping, one must consider the influence of the giant planets, and especially Jupiter. The mass of Jupiter shapes the distribution of small bodies over great distances, creating resonances that stabilize or eject certain objects. The Hungarias reside in a region influenced by 2 major resonances: the long secular resonance Nu-6 and the 4-to-1 resonance with Jupiter, where the asteroid completes 4 revolutions for every single one Jupiter makes. These mechanisms determine trajectories and keep the Hungarias in a stable corridor. Exploring this region, we notice that the Hungarias have higher orbital inclinations than the classic asteroids of the main belt, between 16 and 34 degrees relative to the ecliptic. This angle gives the ring an inclined appearance, visible only through data analysis. This shift in orbital planes helps to understand the dynamics of the entire solar system. These asteroids are often of type E, rich in enstatite, a silicate with high magnesium content. Their surface reflects a lot of light, and the measured spectra reveal precise chemical signatures. These characteristics suggest that the Hungarias have been subjected to high temperatures capable of altering their initial composition. At 1.8 astronomical units, temperatures can exceed 200 degrees Celsius in the most exposed areas, causing significant thermal evolution of the surfaces. The secular stability of the Hungaria ring, which spans millions of years, relies on resonances to form natural barriers that limit the dispersion of asteroids. In the short term, certain objects oscillate slightly in their trajectory, but in the long term, they remain confined, drawing an inclined crown around the Sun. The mechanics of these transformations are also explained by the perturbations from other planets and the Yarkovsky effect, resulting from the re-emission of solar heat by the asteroid. This weak thrust accumulated over long periods can shift bodies either inward or outward of the ring, influencing their precise position. Even though this region is not as dense as the main belt, collisions are frequent. Impacts between asteroids generate fragments and dust clouds that contribute to the zodiacal light, observable from Earth as a glow along the ecliptic. The high inclinations amplify the relative velocities during collisions, producing debris that disperses and then spirals towards the Sun under the pointing Robertson drag. Analyzing these grains through space instruments or ground telescopes allows tracing back their origin. We now enter the vast main belt of asteroids, which extends from about 2.1 to 3.3 astronomical units from the Sun. This ring groups rocky and metallic blocks, remnants of the initial formation of the solar system. Often perceived as a mere boundary between the terrestrial planets and the gas giants, this region actually reveals a great variety of objects, trajectories, and compositions. To grasp its richness, it is first necessary to describe its subregions, then to detail the variation of materials depending on the distance to the Sun, before considering the influence of dynamical gaps, collisions, and asteroid families on its structure. The main belt is divided into 3 major zones: inner, median, and outer. The region closest to the Sun, between 2.1 and 2.5 astronomical units, is dominated by S-type asteroids, whose silicate surfaces reflect a lot of light. These rocky bodies appear relatively bright and reflect solar radiation, illustrating the mineral composition of the warm part of the ring. As we move towards the median zone, Between 2.5 and 2.8 astronomical units, C-type asteroids become more numerous. These dark bodies, rich in carbon and sometimes hydrated minerals, reflect little light. They are true time capsules, potentially containing water and organic matter that may have been brought to the inner planets in the early times of the solar system. In the outer part, from 2.8 to 3.3 astronomical units, P-type and D-type asteroids appear, even darker and often porous, rich in organic compounds or volatile ices. These objects formed far from the Sun and slowly drifted toward their current orbits. This transition in composition, from bright S-types to dark P and D-types, reflects a chemical gradient associated with decreasing temperatures as one moves away from the Sun. The main belt is not a uniform ring. Gaps, called Kirkwood gaps, mark unstable orbits subjected to resonances with Jupiter. When an asteroid occupies such an orbit, small perturbations accumulate and cause it to drift into other orbital pathways, or even propel it toward the inner planets, creating near-Earth asteroids. These gaps thus sculpt the ring and define its dynamic boundaries. This transport to orbits close to Earth also represents a scientific opportunity and a challenge for planetary protection, allowing the assessment of collision risks and the design of potential deflection strategies. The thickness of the main belt reflects the diversity of orbital inclinations. Unlike a thin ring, its asteroids evolve at different angles, leading to frequent collisions. These impacts generate a cascade of fragmentation, producing numerous debris particles, the finest of which contribute to the zodiacal cloud, a veil of dust diffusing sunlight in the inner solar system. Thermal imaging, in wavelengths of 10 to 20 micrometers, allows for the study of the thermal inertia of these bodies, revealing the porosity and cohesion of their regolith. A porous surface heats up and cools down quickly, while a compact surface better balances temperature variations. These observations, complemented by radar and spectroscopy, illuminate the internal structure and mineral composition of asteroids. Some asteroid families, such as those of Vesta, Flora, Eos, or Themis, stem from massive collisions. By analyzing trajectories and compositions, scientists trace the origin of fragments grouped on neighboring orbits. The Yarkovsky effect, which slowly displaces objects by heat emission, allows dating these events and reconstructing the history of the families. All observations show that the main belt is a complex disk, constantly reshaped by Jupiter's gravity, collisions, and micrometeorite erosion. Variations in composition, the presence of gaps, and the dynamics of families illustrate the richness and diversity of this region. The subdivision into inner, median, and outer zones reflects the formation conditions. S-type asteroids in the warm part are poor in volatiles, while C and PD types retain carbon and sometimes ices. Collisions perpetuate the renewal of fragments. Some migrate toward Kirkwood gaps and may approach Earth, ensuring a permanent mixing of matter. In the heart of the asteroid belt between Mars and Jupiter, various debris coexist. One often imagines a vast ring of scattered rocks, but there are also dust and more subtle structures. Among them are rings of debris and cometary trails. These circular ribbons of particles follow the trajectory of certain comets crossing the belt. Short-period comets leave a trail of tiny grains and larger fragments. To detect them, astronomers measure surface brightness, evaluating the sunlight reflected by these dust particles. This light reveals the density, average size, and approximate chemical composition of the wandering materials. Observing these rings requires sensitive instruments and systematic monitoring to distinguish their signature amidst the asteroids. These trails appear thanks to periodic comets. A comet contains ice, volatile compounds, and dust. As it approaches the Sun, the ice melts and releases these particles, forming a diffuse coma and sometimes a visible tail. Some comets cross the main belt between 2 and 3 astronomical units. The emitted particles eventually align with the comet's orbit. Gradually, they form a tenuous ring, detectable through precise infrared or photometric observations. Each passage adds a layer of particles, creating these discrete ribbons. To model the movement of these grains, researchers study the pointing Robertson drag. This phenomenon results from solar irradiation and the grain's orbital motion. Each grain absorbs sunlight and re-emits it in infrared. The uneven emission acts as a light drag, reducing orbital energy and slowly drawing the grain closer to the sun. The smaller and closer the grain is to the sun, the faster the process. This mechanism explains how dust from the belt can migrate to regions near Earth. Some grains come from distant regions, like the Kuiper belt. Comets from Jupiter's family release particles that spread into the belt before continuing their journey towards the inner solar system. Thus, externally sourced dust mixes with local structures, forming ephemeral microrings and diffuse trails depending on the type of comet and emission conditions. Beyond comets, some asteroids in the main belt, called active asteroids, show signs of dust ejection. This activity can stem from the sublimation of subsurface ice or the rapid rotation of the body, expelling surface fragments. Even without significant gas emission, these asteroids create transient rings around their orbit, similar to small comets. To distinguish an active asteroid from a classic comet, astronomers observe the dust trail and analyze the reflected light. These bodies change our perception of the belt, showing it is not just a reservoir of rocks, but a site of particle release. The ephemeral microrings they produce maintain the already existing structures. Researchers aim to quantify dust production and its lifespan. Each cometary passage or asteroid ejection adds materials, but grains are dispersed by collisions, ejected, or drawn inward by the pointing Robertson drag. Mathematical models compare the formation and erosion of trails, while optical and infrared observations allow estimating density, composition, and renewal. Some rings last thousands of years, others disappear more quickly. The lifespan of microrings depends on the orbit and composition of the generating objects. An active comet produces a more pronounced ring, but its dust may erode in a few centuries. An active asteroid produces repeated puffs, forming frequent rings but of lesser extent. Astronomers consider orbital inclination, rotation, proximity to other bodies, and the size of fragments to anticipate ring evolution. Mapping these trails is challenging from Earth, where the zodiacal background can mask cometary rings. Space missions, infrared telescopes, and sensitive spectroscopy help reduce uncertainty. Probes measure in situ density and speed of grains, while photometry and infrared assess their distribution, size, and composition. These observations sometimes reveal unknown rings or discrete collisions. Active asteroids spark particular interest in the study of water in the asteroid belt. If they release ice, they might possess ancient internal reservoirs and have contributed to the delivery of water to terrestrial planets. The traces of carbon compounds suggest latent cometary activity, blurring the boundary between comet and asteroid. Understanding the total mass produced in the belt is a key issue. The production of dust by comets and asteroids allows for the evaluation of the renewal or decline of the grain population. Each observation and each episode of activity contributes to drawing a dynamic picture of the dust. Scientists seek to understand the impact on the longevity of microrings, the thickness of dust, and the population of small bodies in the inner zone of the solar system. These rings and trails reveal the vitality of the asteroid belt. Active comets and asteroids release particles, forming bands that migrate inward into the solar system under the effect of the pointing Robertson drag. From detection to modeling, researchers aim to grasp the evolution of these microrings, linking the infinitesimal grains to the overall destiny of an entire ring. The main belt is not immutable. Every fragment can become a new chapter of cosmic history. The Ceres zone, located between 3.3 and 3.7 astronomical units, borders the main belt. Beyond the 2.1 resonance gap with Jupiter, this area is less populated. The objects residing there are often of type P or D, with dark surfaces rich in organic materials. Named after asteroid 65 Cybele, this zone attracts researchers seeking to understand the distribution of bodies as one moves away from the Sun. The light spectra sometimes reveal water ice in depth, more stable in this cold region where the temperature can drop around 100 degrees Celsius. The dark materials originate from ancient cosmochemical processes, where particles aggregated and then migrated to the edges of the belt. The Cybele zone shows a notable rate of binary systems, two bodies orbiting a common center. Their presence is detected through periodic variations in brightness. The low density of collisions favors the survival of these pairs, while complex rotation, or tumbling, can result from impacts or uneven sunlight effect, influencing surface activity and orbital evolution. This zone maintains dynamic links with other external populations, like the Hildas, positioned in a 3.2 resonance with Jupiter. Some hypotheses suggest a connection between D-type asteroids and Jupiter family comets, indicating a possible continuum between these bodies. The dust arcs created by micro-impacts offer ring-shaped or arc structures, sometimes durable if orbital conditions are stable. The grain dynamics depend on their size and initial velocity. The finest are quickly pushed away by solar pressure. The more massive ones remain in orbit or gradually disperse. These arcs could form mini-rings indicative of low activity on these distant asteroids. The Cybele zone constitutes a transition space toward the outer ring, linking the main belt to the Hildas and Jupiter Trojans. The density is lower there, but the compositional diversity remains rich. Spectral analyses indicate the presence of organic molecules and modified silicates. The zone could act as a buffer reservoir, accumulating fragments and redistributing them outward, offering a glimpse into the primitive conditions of the solar system. Exploration of this area could intensify with new missions and probes. Spectrometry, thermal mapping, and polarization observation will enable a better understanding of the composition and internal structure of asteroids. The detection of ice or organic materials would provide crucial information on primitive chemistry. Improving remote observations will help catalog binaries and characterize rotations. Understanding this sparsely populated yet enigmatic area will shed light on the genesis and diversity of asteroid rings and explore new avenues on the emergence of primitive life. As we enter the zone where the mysterious asteroids of the Hilda family orbit, we gradually leave Jupiter's orbit to explore a region little known to the general public. These bodies, located about 3.97 astronomical units away, are linked to Jupiter by a gravitational resonance called 3:2. For every 3 revolutions around the Sun, Jupiter completes 2. This synchronization creates a coherent and fascinating set, forming the Hilda resonant ring. We can imagine this ring as an almost perfect polygon that over time takes the shape of a triangle with 3 large areas of asteroid grouping. These clusters, called lobes, follow a slow trajectory around the Sun while avoiding proximity to Jupiter. The subtle balance between solar gravity and the pull of the gas giant maintains this stable configuration. On orbital maps, the concentration points are placed about 120 degrees apart, outlining a triangle that moves gently over time. This resonance is essential for understanding the secular stability of the ring. The cohesion of these asteroids over tens or hundreds of millions of years comes from the dance they perform with Jupiter, which limits violent disturbances. Their precise position and solar gravity create a harmonious balance. The Hildas remain grouped, forming an almost immutable diffuse ring on the human scale. This stability contrasts with other asteroids often disturbed or ejected by Jupiter. For the Hildas, resonance acts as a protective lock. The synodic periods, separating 2 similar configurations with Jupiter, are long, contributing to the regularity of their movement. Their ballet around the Sun appears calm and almost frozen, although it is in fact in perpetual motion. Spectroscopic analysis of the surfaces reveals D-type asteroids, with red hues leaning towards brown. This indicates materials rich in organic compounds and ices altered by radiation. This feature, shared with Jupiter's Trojans and some cometary nuclei, suggests distant origins, perhaps in the trans-Neptunian zone, where bodies incorporate ice and organic compounds, colored and transformed by radiation. These red surfaces allow for a possible origin scenario. The Hildas could be fragments of small bodies formed farther out and migrated towards the inner solar system before being captured by Jupiter's resonance. Their orbital synchronization allows them to stabilize and adopt a common choreography. Spectral similarities with comets indicate that they form a link between these and rocky asteroids. The ring is not fixed for eternity. Interactions with Jupiter vary slightly with each revolution, introducing slow, chaotic diffusion. Astrometric surveys and velocity measurements show slight variations that, over thousands or millions of years, can make some asteroids leave their resonance zone. These movements can bring the Hildas closer to Jupiter, modifying their orbit and propelling them either towards the Sun or to more distant areas. Some become comets of the Jupiter family, with outgassing and visible activity. This transition from asteroid to comet illustrates the continuity between these classical categories. The distribution in inclination explains why the Hildas remain confined to a limited volume. The angle of their orbital plane relative to the ecliptic remains moderate, causing a slight thickening of the ring. The gravitational balance between Jupiter and the Sun maintains relatively inclined, but not very eccentric orbits. Astronomers compiled data over several decades to map the density of the Hildas according to inclination, eccentricity, and distance from the Sun, cross-referencing these observations with computer simulations. These models predict future evolution. The majority will remain in 3-2 resonance, while a fraction will drift to other orbital zones. In practical terms, a journey to this ring would reveal a space where the Sun shines less than near Earth, but sufficiently illuminates the asteroids. Temperatures sometimes drop to 150 degrees Celsius, and surfaces are slowly altered by micrometeorites and cosmic radiation. The environment remains peaceful compared to more densely populated asteroid belts. The Hildas testify to ancient planetary migrations. Past movements of Jupiter and Saturn have altered the distribution of small bodies, and the current Hildas are those preserved in resonance. Their composition offers clues about the chemistry and dynamics of an era we could not observe directly, shedding light on the structure and distribution of materials over the ages. The reddish color also reveals tholins, complex organic molecules formed by exposure to ultraviolet and energetic particles. This confirms a distant formation at the edges of the solar system, followed by a dance of disturbances and resonances that led them to the 3-2 resonance with Jupiter. The Hilda ring is not a continuous ribbon, but a diffuse set of asteroids on coordinated orbits. On a large scale, the triangle with its 3 lobes stands out, illustrating the silent elegance of this stable resonance. Finally, slow, chaotic evolution remains crucial. While the majority of Hildas will remain in place for millions of years, some will escape the resonance. Some will become Jupiter's comets with outgassing. Others will be ejected to the periphery of the solar system. These varied trajectories illustrate the fascinating diversity of matter in our cosmic neighborhood. Observing the Hilda ring reminds us of the richness and complexity of the connections that unite every asteroid, planet, and grain of dust in a ballet orchestrated by gravity and time, which we continue to discover. The Trojans of Jupiter are a fascinating group of small bodies located at the Lagrange points associated with the giant planet. These points lie on Jupiter's orbit around the Sun, about 5.2 astronomical units away, and are divided into 2 main areas, one ahead of Jupiter and the other trailing behind. These are often referred to as the Greek and Trojan clouds, names inherited from epic heroes, as if 2 armies accompanied Jupiter on its celestial journey. Astronomically, these groups form 2 co-orbital half-rings, sharing the same orbital period as the planet, thus remaining captive in their gravitational wells. we will explore the formation of these groups, their properties, and the scientific methods used to study them. Let us start with the notion of orbital resonance. The 1/1 resonance means that each time Jupiter completes a turn around the Sun, the Trojan asteroids do the same, maintaining fixed relative positions, as in a synchronized dance with the planet. In the solar system, these resonances stabilize many objects. The gravity of the planet acts as a cosmic shepherd around the Lagrange points L4, 60 degrees ahead, and L5, 60 degrees behind. The L4 group, or Greek camp, appears more populated than L5, or Trojan camp. This asymmetry could result from gravitational perturbations, collisions, or an uneven initial capture during the solar system's formation. The Trojan asteroids do not just form point groups, they also generate a co-orbital dust ring around Jupiter, much less dense than the rings of planets like Saturn. The optical density of this ring is very low, as the grains, about a micrometer in size, are dispersed and subject to micrometeoritic impacts, renewing or dispersing the dust. To map them, astronomers use infrared imaging, revealing the heat of the grains and their distribution in the ring. The spectral composition of the Trojans has been intriguing for a long time. The majority D and P types indicate darkened and reddened surfaces, likely rich in carbon compounds and organic matter. These objects may contain deep ice protected by the regolith and distance from the Sun. Temperatures can drop to -120 or -150 degrees Celsius. Polarimetry, which measures polarized light, helps determine the composition and texture of the surface grains. Among the remarkable discoveries are binary systems, such as Patroclus and Menoetius, orbiting each other near the L5 point. Their study allows for mass and density measurement, sometimes indicating porous bodies or loosely bound aggregates. These systems provide clues about the primordial aggregation of materials in the protoplanetary disk surrounding the young Sun. To deepen the geology of the Trojans, space missions fly over these asteroids to analyze relief, morphology, and regolith. This surface layer mixes mineral grains, carbon particles, and potentially ice. Some craters, not much exposed to the Sun, can retain ice for long periods. The surface sometimes features ridges, remnants of impacts or gravitational uplifts, and thermal variations affect dust distribution. Thermal stability and gravitational resonance are crucial to maintaining dust in the Trojan orbit, despite disruptions from solar radiation and impacts. Radiation forces, even weak ones, alter the trajectory of the grains. The influence of Jupiter adds extra complexity in the dynamic modeling of these particles and the co-orbital ring. Remote exploration remains a captivating objective. Spacecraft could fly over or land on these asteroids, measure the regolith's composition, the buried ice, and map craters and ridges. Infrared and optical instruments would quantify dust density and characterize the co-orbital ring. Polarimetry and radar would provide complementary information on the texture, porosity, and composition of the grains. Binary systems like Patroclus and Menoetius offer a direct glimpse into the processes of aggregation and rotational separation in the primitive solar system. Observing their current configuration helps understand how these mini-rings of residual matter form or disperse. Centaurs are small, icy bodies evolving between 5 and 30 astronomical units from the Sun. At these distances, sunlight is weak and temperatures very low, often around -200 degrees Celsius. Their name comes from Greek mythology, symbolizing their hybrid nature between asteroid and comet. They form a diffuse, extensive, and unstable ring. Their trajectory is chaotic under gravitational influence, located between Jupiter and the Kuiper Belt. Some migrate towards the inner solar system and become short-period comets, while others are ejected or captured in distant orbits. Their average lifespan is a few million years. The population is constantly renewed from trans-Neptunian reservoirs. Some centaurs possess rings, like Chariklo, detected by stellar occultation. This method measures the drop in brightness of a star when a body hides it. Cherry Glow presents two narrow rings, whose width, opacity, and precession have been measured. This discovery surprised the scientific community, which thought only large bodies could maintain enduring rings. Collisions, rotational fissions, or gravitational resonances with satellites could explain their confinement. Chiron might also have a ring, but the evidence is less certain. Repeated observation, through occultation or infrared spectroscopy, is necessary to confirm its presence. The formation and evolution of these rings depend on collisions, shepherd satellites, and the collisional viscosity that regulates interactions between grains. The composition of the grains includes water ice and tholins, organic molecules coloring objects red or brown. Near-infrared spectroscopy is used to identify these compounds. The electric charge of the particles, influenced by the solar wind, creates electromagnetic forces that alter the movement of the grains, especially around small bodies where local gravity is weak. Centaurs illustrate the transition between objects close to Jupiter and those located further in the Kuiper Belt. The flow of bodies from outer regions mixes with those influenced by giant planets, creating a blend of varied compositions, ice, rocks, and organic elements. Some become comets, developing gas jets and dust trails along their orbit. Cherclo and Chiron may not be the only examples. Other centaurs could host small, temporary rings. Each occultation, or spectroscopic observation, provides information on the density, distribution, and size of the grains. The study of these rings sheds light on the circulation of ice and dust in the solar system and the fate of intermediate objects. The comets of the Jupiter family make up a captivating group of objects traveling in the inner solar system. The origin of these comets lies in the trans-Neptunian region, mainly in the Kuiper Belt, a vast belt of icy asteroids beyond Neptune. Some objects are ejected toward the inner solar system by the gravitational influence of the giant planets. Over time, some acquire a Tesserain parameter greater than 2 and an orbital period of 20 years or less, classifying them in the Jupiter family. The proximity to Jupiter leads to significant gravitational interactions, altering their trajectories and eccentricity. Eccentricity indicates how much the orbit deviates from a perfect circle, from nearly circular to very elliptical. A key characteristic of these comets is their orbital plane, often close to the ecliptic, where Earth orbits the Sun. Sublimation releases dust that varies in size, from micrometers to millimeters. The larger grains form trails along the orbit, while the finer ones disperse under the influence of the solar wind, creating a diffuse coma around the nucleus. This diversity allows for mapping the dust distribution in infrared imaging. Non-gravitational accelerations related to the ejection of gas and dust exert an asymmetrical push that can alter the orbit. Over successive perihelion passages, these effects change the structure of the dust rings. Modeling these jets helps predict the distribution of the material and assess collision risks with Earth. The comet's rotation also influences the direction of emissions. Infrared imaging allows for measuring the mass of dust trails, their density, and their composition. It reveals activity peaks when sublimation accelerates as it approaches the Sun. The dust crossing Earth's trajectory generates meteor showers, whose frequency and intensity are linked to these swarms. Over time, some comets fragment, leaving several smaller nuclei on similar orbits. These multi-rings raise questions about potential impacts on Earth, even though most particles are too small to cause damage. The trajectories of the fragments are tracked by numerical models to anticipate possible encounters. Tempel 1 illustrates these phenomena. With an orbit of 5.5 years, this comet was studied during the Deep Impact mission, which created an artificial crater and released dust and gas, revealing the presence of silicates, ices, and organic molecules, testifying to primitive materials of the solar system and layered structures, signifying a complex geological history. The comet, 67P, Churyumov-Gerasimenko, or 67P, completes a cycle of 6.5 years. The Rosetta mission highlighted its bilobed shape and a seasonal activity. Localized jets release particles a few centimeters in size, while other areas remain calm. Complex organic compounds show that these primitive bodies could have transported material to the planets. Enki, with the shortest known orbital period, about 3 years, is associated with the Taurids, whose dust generates visible swarms each autumn. These observations show the influence of Jupiter and non-gravitational forces on the trajectory of comets and the formation of debris rings. Halley-type comets, or Halleyan comets, possess distinct orbital and physical characteristics, influencing the formation of debris rings and meteor showers. Their Tisserand parameter with Jupiter is about 2, indicating a particular interaction with the gas giant. They present high inclinations and sometimes retrograde trajectories, leading to high-speed encounters with the particles of the solar system. Meteor swarms, like the Orionids or the Eta Aquariids, originate from dust emitted by these comets over the centuries. The sublimation projects grains that spread along the orbit, and when Earth crosses them, they give rise to meteor showers. The angle of the orbits and the relative speed explain the dynamics and brightness of these phenomena. As they pass by the Sun, Halley-type comets lose their activity and become dark, similar to D-type asteroids. They continue to produce secondary dust during collisions, and the meteoroid rings can be occasionally replenished. The ejection speed of the particles varies according to their size. The smallest ones move away quickly, while the larger ones remain close to the nucleus, sometimes producing spectacular fireballs. The lifespan of the rings depends on gravity, planetary perturbations, and the Poynting-Robertson drag, which slowly spirals the particles toward the Sun. Without replenishment, these swarms disperse over thousands to tens of thousands of years, but active comets, or occasional reactivations, can resupply them. These comets act as bridges between different objects in the solar system, dynamic and bright, or dark and amorphous. Their rings, formed by dust ejection, create inclined circles that the Earth can pass through, illuminating the sky with the Orionids, the Eta Aquariids, and other meteor showers. The persistence of these rings is governed by gravity, close encounters, solar drag, and residual cometary activity. Astronomers, space engineers, and meteor observers contribute to a better understanding of these phenomena. Over millennia, these Halley-type comets and their rings may disperse, but for now, they offer an ephemeral and fascinating spectacle, reminding us that each dust particle and each comet is part of the common history of the solar system. The Kuiper Belt, also called the Trans-Neptunian Ring, stretches well beyond Neptune. It is a vast territory where countless icy worlds orbit in darkness. This ring-shaped region gathers fragments of rocks and ice that orbit the Sun. To understand this place at the edge of the solar system, one must explore its content, structure, and history. We will discover the different categories of objects residing there, its thickness, its density, and the phenomena that have shaped it. It is a journey both scientific and imaginative to the heart of a still unknown area, rich in mysteries. 3 main families of objects are distinguished, classified according to their orbital characteristics. The first group includes cold classical objects. The term cold suggests not only their distance from the Sun and temperatures below -200 degrees, but especially the low inclination of their orbits relative to the main plane of the planets, called the ecliptic plane. These objects thus evolve in a relatively flat ring. Many of them are considered primordial, preserved since the birth of the solar system. Their study helps reconstitute the chemical and physical history of the solar nebula, this vast cloud of gas and dust that gave birth to the Sun and its planets. The second group consists of resonant objects. They are linked to Neptune by regular gravitational interaction. Plutonos, for example, follow a 3-to-2 resonance, while Teutinos evolve in a 2-to-1 resonance. These mechanisms act like locks that stabilize certain orbits over billions of years. Pluto is the emblematic example, but hundreds of other worlds share this behavior, forming a particular subset of the belt. The third group gathers the so-called hot objects. Here, the term refers to the high inclination of their orbits. Unlike cold classical objects, they deviate significantly from the ecliptic plane, forming a thicker and less regular ring. Their trajectory reflects an agitated history, gravitational perturbations, planetary migrations, or encounters with Neptune. These events have scattered numerous bodies into inclined or eccentric orbits. Beyond this classification, the Kuiper Belt reveals other characteristics. Its thickness varies depending on the region. The cold population forms a thin layer, while hot objects significantly expand the disk. Its matter density, called surface density, also changes according to the distance to the Sun. There are gaps, areas depleted of objects, due to unstable resonances with Neptune. These gaps find their origin in the history of giant planets. Models show that initially their orbits were tighter. As Neptune migrated outward, it pushed away many small bodies, some trapped in resonances, others ejected. The belt bears the mark, a disk punctuated by grooves, concentrations, and structures testifying to the solar system's turbulent past. Some objects particularly attract attention. Among them are the cold binary systems, two bodies orbiting a common center. Arrokoth, flown over by the New Horizons probe, is a remarkable example. Its bilobed shape suggests a gentle collision, indicative of the calm conditions that prevailed during its formation. These binaries inform us about the assembly mechanisms in the early solar system. Haumea is another fascinating object. This dwarf planet, with an elongated shape, rotates on itself in less than 4 hours. Its rapid rotation gives it the appearance of a flattened ellipsoid. It possesses a narrow ring, discovered through stellar occultations. This structure is thought to result from an ancient impact that ejected debris, which stabilized into a circle of matter. Studying Haumea and its collisional family sheds light on the effects of violent impacts in the trans-Neptunian region. Quaoar intrigues with the presence of a ring located beyond the Roche limit, where debris should typically coalesce into a moon. Its stability remains mysterious. Researchers propose several hypotheses: gravitational resonances, particular cohesion of particles, or dampened collisions preventing satellite formation. The evolution of this ring presents a major challenge for current models. These examples reveal the diversity of the Kuiper Belt. Contrary to science fiction images, it is not a zone saturated with closely packed objects. The space is vast, even though the distribution of bodies is uneven. Neptune's dynamics, collisions, and orbital history have shaped a complex ring where tiny fragments coexist with worlds hundreds of kilometers across. Spectral observations reveal the composition of these bodies: water ice, methane, and tholins, those organic compounds giving reddish hues to certain surfaces. These clues help distinguish the cold population from the hot population, offering insights into their origin and evolution. The discovery of rings around bodies like Haumea or Quaoar opens a new chapter. Long associated with giant planets, these systems now also appear around small worlds, raising new questions about their formation and stability. Each new ring discovered allows us to test our physical models and push the limits of our knowledge. The Kuiper Belt is also a reservoir of comets. Some of its objects can be deviated and plunged towards the inner solar system. Others are linked to the scattered disk or the even more distant Oort cloud. Each observation enriches our understanding and links these populations together. Exploration progresses thanks to telescopes and space missions. New Horizons, with its flyby of Pluto and Arrokoth, has offered unprecedented images and a better understanding of surfaces, compositions, and dynamics. Other instruments will refine this vision, revealing new rings, new families of objects, and perhaps unsuspected systems. Ultimately, the Kuiper Belt is not just a frozen periphery. It testifies to a time when giant planets sculpted their environment. It illustrates the diversity of possible trajectories and orbital histories. It is a shifting frontier of knowledge where each discovery poses new questions. It is both a distant landscape and a natural laboratory. It teaches us how matter assembled, dispersed, and sometimes stabilized into unexpected rings. It shows us that collisions can be gentle, that fast rotations shape strange bodies, and that laws once thought universal can be contradicted. The Kuiper Belt is an open book about the infancy of the solar system, and we are just beginning to decipher its pages. Our exploration continues, and with each step, new worlds are unveiled, bearing the secrets of origins. Imagine an immense space at the far reaches of the solar system, so distant and dimly lit that it seems plunged into an icy night. In these extreme regions, celestial objects follow very elongated paths, spending most of their time far from the sun. This area, where numerous objects with eccentric orbits gather, is called the scattered disk. At first glance, one might think of it as an extension of the Kuiper Belt, which houses worlds like Pluto. However, the scattered disk is distinguished by particularly strong orbital eccentricities. This dynamic outlines a vast, deformed ring, shaped over time by gravitational forces. At its periphery, there are also detached objects, seemingly suspended in space, whose orbits tell an even more mysterious story. To understand their nature, one must recall what an eccentric orbit is. It is an oval path around the sun, with a point of proximity and a point of extreme distance. The minimum distance to the sun is called the perihelion. In the case of objects in the scattered disk, this perihelion is often high, keeping them distant from the giant planets. But their orbits are so extensive that some, subjected to subtle perturbations, can approach the inner solar system and then be cast back outward. This back and forth, over millions of years, fuels a flux of celestial bodies that sometimes venture as far as the giant planets or adopt comet-like trajectories. When one of these bodies crosses the zone between Jupiter and Neptune, it is classified among the centaurs, halfway between asteroids and comets. Those that delve even further inward, developing a coma and tail, become Jupiter family comets. The extended and broken ring of the scattered disk is explained by gravitational diffusion. The giant planets, revolving around the sun, exert forces that gradually alter the orbits of small bodies. Some areas offer relative stability, others great instability. Gradually, these influences displace the objects into increasingly eccentric or inclined orbits. Some end up totally detached, with perihelia so distant that they never approach Neptune or Uranus. Among them, Sedna is emblematic. Discovered in the early 2000s, this dwarf planet follows an extraordinarily elongated orbit, with a perihelion far greater than that of Pluto. At its most distant point, it reaches several hundred astronomical units. Such a trajectory cannot be explained by the known planets alone. Researchers therefore consider an ancient event, the passage of a star close to the sun, or the existence of an as-yet undiscovered planet, very far away. Other similar objects, called Sedna-like, share these extreme characteristics, reinforcing the idea of an external influence. These out-of-the-ordinary orbits fuel the hypothesis of a Planet 9. According to certain simulations, its gravity could align the perihelion arguments of objects like Sedna. This orbital angle, called omega, designates the precise spot where a celestial body comes closest to the sun. The fact that several objects show similar values suggests a common cause. However, other researchers support the idea of an ancient stellar flyby, capable on its own of stretching these orbits billions of years ago. To decide, it is necessary to analyze in detail the orbital parameters of a large number of objects. If the angles show a clustering, a global influence is likely. If, on the contrary, they are scattered, it would rather be individual events. Thus, the scattered disk appears as a vast crown of diffuse celestial bodies, with no clear boundary, much more sparse than the Kuiper Belt. Its inhabitants follow varied trajectories. Some drift outward, others venture inward. It is a reservoir where Centaurs and Jupiter family comets are born. These bodies, having remained in extreme cold for billions of years, have preserved a primitive chemistry that illuminates the history of the solar system. Numerical simulations show how these transfers operate. Under Neptune's influence, the orbits change slowly, sometimes over millions of revolutions. Some bodies eventually cross paths with Uranus or even Jupiter, while others are temporarily captured in resonance. These dynamics, invisible on a human scale, nonetheless constitute a constant ballet on a geological scale. To unravel this scenario, astronomers study the distribution of the arguments of perihelion. If a clear grouping appears, it will argue for the existence of a hidden planet or a not yet well understood resonance. A random dispersion would rather indicate various influences, such as galactic tides or the passage of ancient stars. Observing these bodies remains a challenge. Tiny, dark, and distant, they require powerful telescopes. Astronomers scan wide fields, search for faint points of light, then patiently confirm the orbits through repeated observations over several years. Many, like Sedna, have not even completed a full revolution since their discovery. The stakes are immense. Understanding these orbits illuminates not only the history of the scattered disk, but also that of the formation of the solar system. Detached objects reveal an invisible architecture, where each orbital parameter is a piece of a cosmic puzzle. Astronomers continue their investigation, observation after observation, hoping to reveal whether these isolated worlds are mere witnesses or the missing keys to a larger cosmic narrative. Imagine navigating through a vast array of particles orbiting a central body, whether it is a giant planet or a small celestial object. Around you float both tiny grains a few micrometers in size and blocks occasionally exceeding a kilometer. Together, they compose a strange and fascinating landscape. Rings sometimes dense, sometimes diffuse, sometimes so thin that they seem almost invisible. Yet these myriad grains obey multiple physical laws. They testify to a complex dynamic, governed by gravity, by incessant collisions, and by other forces that do not directly pertain to gravitational attraction. On this journey, we will explore the mechanisms at work in these rings, addressing key notions such as the Roche limit, collisional viscosity, internal perturbations, heating, and even the ephemeral structures created by mutual gravity. We will also see the influence of non-gravitational forces, such as solar radiation or electromagnetic fields, which shape the size distribution of grains from micrometer to kilometer. Finally, we will discover how sources of particle replenishment, whether impacts, jets of matter, or object fragmentation, ensure the maintenance of these rings. To conclude, we will see how spectroscopy reveals the chemical composition of these grains and, through it, the secrets of their origin. When observing a ring, an essential question arises. Why don't the grains assemble into a moon or fall onto the central star? Part of the answer lies in what is called the Roche limit. It is a critical radius beyond which a body can remain united by its own gravity in orbit around a more massive object. Within it, the tidal force exerted by the central body exceeds the mutual attraction of the grains. A satellite too close will then be shredded, feeding a ring of debris. This radius depends on the respective densities of the bodies involved. There is no clear boundary. Internal cohesion and the presence of ice can allow aggregates to survive slightly beyond this limit. Once the grains are in a ring, they do not remain immobile. They constantly come into contact, sometimes gently, sometimes brutally. These collisions play a fundamental role in the evolution of the structure. At each impact, the grains exchange energy and momentum. This is what is called collisional viscosity. These repeated frictions produce slight heating, converting part of the orbital energy into heat. Even if the overall temperature remains extremely low, this local heat can modify the size of ice grains or weaken certain mineral structures. In dense rings, another spectacular phenomenon occurs, the formation of structures called self-gravity wakes. The mutual gravity of the particles causes them to organize into temporary clusters. These groupings appear, disperse, then reform further on. For an observer, this would resemble filaments or waves stretched by rotation. These structures influence the distribution of grains, intensify collisions, and even alter how light is scattered by the ring. Gravity is not the only force at play. Other forces intervene, particularly on the finer grains. Sunlight, through an effect known as the Poynting-Robertson drag, can gradually slow down or speed up their movement, pushing them toward the inner part of the solar system. Magnetic fields also exert their influence. Electrically charged particles can have their trajectories deflected. Furthermore, the sun's radiation pressure acts as a subtle push, depending on the size and the ability of the grains to reflect or absorb light. The result is a sorted distribution. The smallest grains migrate quickly, while the massive blocks remain more stable. These rings should disappear over time, subjected to collisions, migrations, and losses. However, they persist thanks to constant replenishment. Microimpacts constantly eject clouds of particles. Larger collisions can fragment entire bodies, especially when too rapid rotation ends up breaking them apart. Some active moons or icy bodies also release jets of vapor and dust that continuously feed the rings. Thus, despite the losses, new particles continuously enrich them. We have reached the edges of our journey, where the trans-Neptunian ring gradually fades away to give way to a vast shell called the Oort cloud. At this stage, the matter orbiting the Sun transitions from a relatively flat ring configuration to an almost spherical shell that surrounds the solar system at staggering distances. To understand this transition, one must examine the geometry of the distribution of bodies, the mechanisms of dust supply, the mass constraints, and the historical legacy related to planetary evolution. The Oort cloud is distinctly different from a simple ring of small bodies. A ring concentrates its objects in a plane close to the ecliptic, where Earth and most of the planets orbit. The Kuiper belt, located beyond Neptune, is a good example of this type of configuration, with its multitude of icy objects, whose density varies according to distance and inclination. But beyond several thousand, even tens of thousands of astronomical units, the bodies cease to confine themselves to a flattened plane. They disperse in all directions, forming a vast sphere, still theoretical, associated with the Oort cloud. This reservoir is often divided into two regions, an inner zone and an outer zone. The inner part sometimes extends the Kuiper belt, but in a dilated and irregular form. It is not perfectly spherical because, over time, passing nearby stars or the gravitational field of the galaxy have disturbed the orientation of the orbits. These residual imbalances, called anisotropies, still bear witness to the dispersion mechanisms that shaped the region. To estimate the mass of the Kuiper belt and the Oort cloud, astronomers observe comets and the light of distant dust. Every comet that approaches the Sun releases grains, providing a clue to its origin. By compiling their frequency and trajectory, one gradually deduces the amount of material in reserve. The infrared brightness or the occultations of stars provide other measures of the distant dust. Compared with gravitational diffusion models, they allow refining estimates of cumulative mass. These data provide the radial profile of the dust density from within the solar system to the icy regions located tens of thousands of astronomical units away. They study the evolution of particle flux, the size of the grains, and their composition. It is a matter of distinguishing what comes from asteroids, comets, or even interstellar microimpacts. In this panorama, the chemical and thermal gradient plays a central role. The farther from the Sun, the more the temperature drops, preserving volatile ices like water, nitrogen, methane, or ammonia. Beyond 40 astronomical units, sublimation becomes almost non-existent, and the grains often consist of complex organic materials and colored tholins. In the Oort cloud, these cryogenic materials are even more abundant, direct vestiges of the formation of the solar system. In the beginning, a vast protoplanetary disk surrounded the young Sun. The migrations of Neptune and Uranus pushed away or captured a multitude of planetesimals. This reorganization sculpted the Kuiper belt and projected some of the objects into distant orbits, giving rise to the Oort cloud. Early gravitational instabilities amplified this process, creating a spherical reservoir linked to the convulsions of the early solar system. Similar observations appear around other stars, where dust disks reveal analogs to our own reservoirs. By comparing their organization to that of the Kuiper belt or the Oort cloud, we reconstruct the universal steps of planetary formation. What initially is just a simple ring can become a vast reservoir shaped by collisions, migrations, and gravitational perturbations, eventually forming a shell like that of the Oort cloud. To refine this picture, astronomers map the trans-Neptunian population and measure the light scattered by the grains. These surveys provide information about the total mass, the proportion of ice and rock, the size of the particles, and their origin. The difference between the ring and the shell is apparent in the dynamics of the orbits. In the Kuiper belt, many objects maintain moderately inclined trajectories, but in the Oort cloud, the orbits become very eccentric and extend to tens of thousands of astronomical units, creating an isotropic halo encompassing the entire solar system. A major challenge remains in estimating the total mass of these reservoirs. Estimates vary because these bodies are small, distant, and dimly lit. Models, however, suggest a cumulative mass equivalent to several tens or even hundreds of times that of Earth. The uncertainties stem from the small observable fraction and the complexity of light diffusion phenomena. All of this shows an equilibrium in constant evolution, a memory of the early solar system. The boundary between the trans-Neptunian ring and the Oort cloud is not clear. A transitional zone gradually shifts from a flattened plane to an almost isotropic sphere. This transition reflects billions of years of history and the influence of the galaxy. The composition of the grains betrays this memory, revealing how matter has circulated since the birth of the sun. As for the origin, researchers agree on a mix of planetary migration, gravitational instabilities, and heritage from the protoplanetary disk. Comparisons with the disks observed around other stars confirm the universal character of these mechanisms. The nearby ring reflects a tumultuous youth, while the distant shell is its culmination. These large reservoirs are the farthest witnesses of the history of our solar system. In the coming years, observations will aim to refine the distribution of small bodies and the composition of grains. The more the uncertainties about the mass of these reservoirs are reduced, the more our understanding of solar genesis will progress. This journey, from the warm to the icy, reveals much more than just an inventory of objects. It sheds light on the physical and chemical mechanisms that have shaped our solar system. The outskirts, bathed in an immutable silence, preserve the secrets of a vast continuum between icy rings and ghostly envelopes, the ultimate legacy of our star's childhood. And beyond, what lies after these icy boundaries, after these silent reservoirs where the vestiges of the past slumber? What will we discover once this thin boundary between the sun's light and interstellar darkness is crossed? This is the journey into the unknown that we will now undertake.